So section 7.8, solving trig equations number 2, is essentially the identical section to 7.7, is just an extension. Some of the equations are a little bit more difficult. Some of them involve some factoring, some quadratics, and other things that come from previous sections in order to get the variable by itself. Your learning targets are: I can solve trig equations in factored form, I can solve trig equations in quadratic form, and I can solve trig equations using identities. So we have 5 examples today. The first example, example 1, is cosine of theta times the quantity of 2 cosine theta minus 2. Now, since this is already in factored form, I can take the two factors and I can solve them separately. So I have the zero product property would say that since this is equal to 0, I could either say cosine of theta equals 0, or 2 cosine theta minus root 2 equals 0. I can say them separately and I can solve them. This one is already done. Let's add root 2 to both sides and get 2 cosine theta equals root 2, and then divide both sides by 2, which means cosine of theta is root 2 over 2. And then I jump over to the circle and I find out where are the values, where are the x and y values that make all of these true. In this case, cosine is 0. At what angle is cosine equal to 0? There are 2 of them, and it is at pi over 2 and 3 pi over 2. And what are the x values of theta that are root 2 over 2? Well, the x values of theta are going to be pi over 4, has an x value of root 2 over 2, and also 7 pi over 4. All right, so we have a set of answers that look like this. Technically, I can add to it any version of 2 pi of all of these, where k is an integer. So I have infinitely many solutions, but all of the solutions between 0 and pi over 2 are pi over 2. All of the solutions between 0 and 2 pi are pi over 2, 3 pi over 2, pi over 4, and 7 pi over 4. For my next example, we'll call this 2 cosine squared theta minus cosine theta is equal to 1. Now I notice that I have a squared here, right? And then this is technically considered my linear term. You can sort of, in a way, think of this as 2x squared. You don't have to, but I can think of this as 2x squared minus x, right? And now if I were to bring the 1 over to the other side, I can subtract 1 from both sides, and I can sort of essentially factor this using reverse FOIL. And so out in the front, I have a 2x, or I have a 2x squared, or a 2 cosine squared, so we can really call this 2 cosine times cosine, because first times first, 2 cosine times cosine would be cosine squared. My last term is 1, so that would be 1 times 1. The minus on the 1 means that the signs are different, and the minus here goes to the larger number. I'm going to put the minus with the second factor, because the minus goes with the minus 1 goes with the 2 cosine, and the plus 1 goes with the 1 cosine in the middle. And if I were to FOIL this out, this would leave me with a minus x in the middle. Now, essentially what I have are 2 factored forms, and I can solve this as 2 cosine theta plus 1, set that equal to 0. And I can solve this as cosine theta minus 1, and I can set that equal to 0. Minus 1 from both sides, divide both sides by 2. This is going to tell me that cosine of theta is equal to negative 1/2, or cosine of theta is equal to positive 1. So we go ahead and look and see what our solutions are going to be. What angles have an x value of negative 1/2? So I can look at my unit circle and say, all right, the x value is of negative 1/2, and it looks like I have one here at 2 pi over 3. And if I flip down for that x value of negative 1/2, looks like 4 pi over 3. So for my first factor, my solutions are going to be 2 pi over 3 and 4 pi over 3. And again, I'm looking for another x value that is positive 1. And so I go back to my circle, and an x value that is going to be positive 1 is going to be found at 0. So I have 3 solutions for this one that are in the interval of 0 to 2 pi. Example 3, a little bit of a different question here. Secant squared theta plus 6 tan theta plus 4 is equal to 0. Now, learning target number 3 does say that I have to use an identity. That is an option that is on the table that we can use to figure out how to simplify this. And I notice that I have a secant squared and I have a tangent. There has to be an identity that relates the two. And I noticed that in one of my Pythagorean identities, secant squared and tangent are related in that 1 plus tangent squared is equal to secant squared. And if I take this 1 plus tangent squared, I can substitute it into its place, and then I have an equation that's represented by all tangents. So 1 plus tangent squared plus 6 tan plus 4 equals 0. Let's simplify this a little bit. Here's my quadratic term, tangent squared. I can bring down the 6 tan like this, the plus 1 out in the front, and the plus 4 here in the back, make a plus 5, and that's equal to 0. Now we have a quadratic which can be factored. Let's try to factor it like this using reverse FOIL. Tangent squared out in the front is going to be tangent times tangent. What are my factors of 5 that add up to 6? Have to be 5 times 1. And my final solution here in the back is positive, so let's call this plus plus because positive times a positive is a positive. So let's go ahead and solve these two roots. Let's start with this one. This one might be a little bit easier. Here I see that tangent theta is equal to -1. So I want to know where are the values on the unit circle that are equal to -1 for tangent. Well, I know that pi over 4 is positive 1 because y over x, or root 2 over 2 over root 2 over 2 is positive 1. And so I know that all students take calculus would tell me that sine is the positive trig function in quadrant 2, which means tangent is negative, and y over x, or root 2 over 2 over negative root 2 over 2 is going to be a -1, and the same is true in quadrant 4. So those are going to be my two solutions for this one. Let's call that 3 pi over 4 and 7 pi over 4. How about this? If I were to think of this as tangent theta plus 5 equals 0, I could really bring the 5 to the other side like this, and then I could do inverse. There's not an exact answer here, but there is an answer that we need to write, right? So if I take the inverse tan of both sides, I could really write it as inverse tan of -5. These are the three solutions. I mean, I do have 3 solutions, 2 of which are exact, 3 pi over 4, 7 pi over 4, and then inverse tan of -5. This is a decimal in the calculator, which we're not too worried about, but we did go ahead and find one of the solutions to it. Example 4, sine cubed theta equals sine theta. Let's bring the sine over to the other side by subtracting it like this, so we can put them all together, and we're going to see if we can factor this question. The greatest common factor of sine cubed and sine is sine, so we can bring a sine theta out in the front, and I'm left with sine squared of theta. When I divide, sine cubed divided by sine is sine squared minus 1. Now, I have a sine out here in the front by itself. We can leave that there for a minute. This is a difference of 2 squares, so sine squared minus 1 can be factored as sine plus 1 and sine minus 1. And I know that because first times first is sine squared, which we have here. Last times last is -1, which we have here. Outer is minus sine, inner is positive sine, and those would cancel. So I essentially have 3 factors, and we're going to go ahead and solve those separately. So if sine of theta is 0, where is the angle on the unit circle such that the y value is 0? And those would be 0 and pi. I then want to find out where my angles are plus or minus 1. In the first one would be -1 and then +1. So where are the y values that are +1 y value and a -1 y value? And those are found on the unit circle at pi over 2 and 3 pi over 2. Final solutions, we have 4 of them, and they are listed right here. Final example of the day is example 5. Example 5 looks something like this. Sine minus cosine equals 1. Now I talk about this question for a minute because not a whole lot that we can do with this. I could bring the cosine over here. That doesn't get me really anywhere. I really should put my thetas in. Doesn't really matter, but just to see that. There's no real identity that pairs up sine and cosine together. I can't really think of anything that would work for me to simplify this using an identity. But what I can do is I can square both sides, and that would keep things equal. Now, I want to write this as sine minus cosine times sine minus cosine, and that's equal to 1. First times first is going to be sine squared. Outer is going to be minus sine cosine. Inner is going to be the same thing minus sine cosine, which means I have two of them. So I'm going to put a 2 out there in the front. Last times last is minus cosine times minus cosine, which is positive cosine squared, and that's equal to 1. Now let's use another identity to see if we can simplify something here. It looks like my sine squared and my cosine squared can pair up together. I have an identity which says sine squared plus cosine squared is equal to 1. So these are essentially canceled out and equal to 1. And I'm going to bring down my minus 2 sine cosine, which is also equal to 1. Let's simplify this a little bit. Minus 1 from both sides like this. So I have negative 2 sine cosine is equal to 0. Now, this looks like something that we may have seen before. And if you look on page 463, we have a double angle formula which says sine of an angle that's doubled is equal to 2 sine cosine. So essentially that's what we have here. If I divide both sides by negative 1 just to get rid of the negative, I could say that 2 sine cosine is equal to 0, because 0 divided by negative 1 is 0. So 2 sine cosine is equal to sine of that double angle. Let's call this sine of 2 theta, which, by the way, this identity is found on page 463 of your textbook. So you can look there if you don't remember what they are or if you haven't seen them before. Now I can solve the question which says 2 theta is equal to what values? Now what I notice here is that I'm looking for the y values on the unit circle that are 0. There are 3 of them that are between 0 and 2 pi. Normally we wouldn't have to include 0 and 2 pi, but since they are all doubled and I divide all these by 2, I now can see why we have 3 solutions, in this case 0, pi over 2, and pi. So those are my 3 solutions for this question.